Okay, so let's look at a second example and see if we can apply the same techniques. So this one says find the net force, and always when someone asks you force, always magnitude and direction together for the trolley being dragged by two ropes. So it could be just two people dragging them like a tug of war kind of thing, pulling it. They are dragging with different degrees and different tension as well. So on this side, there's 10 newtons of tension. This side is 20 units of tension or force. Tension is just a force by a rope on whatever object. Okay, so first thing, draw a free body diagram. Okay, so this is somewhat like a physical diagram. You see that the ropes are connected to the top, not from the center of mass. We'll always draw the thing right from the center of mass. And it's a good way to have all the reference points just put in your coordinate system as well. Once you put in your frame of reference or your system, that's easier to sort of draw things relative to it. So we have this, which should be an arrow. So that's what I mean by it's like a physical diagram, right? So it's not, the rope can be the same length, but this is tugging harder. So you should draw a longer arrow for this, which is around 60 degrees towards this way. And this should be like just half the length towards this side. So I don't need to be too accurate. I don't need a ruler to measure it in an exam or in your homework, but just relatively get the right size, that's fine, right? So this is 20 newtons this way. This is 10 newtons this way. Let's label all the necessary information over here. Okay, good. And yeah, so this is vector T1. This is vector T2, like this. All right, so now let's add these two together. So we'll find the net force. It's T1 plus T2, like this. Okay. Now, remember, we talked about here, you need to break it into, because these are vectors, vector addition. So you should have components like this. And this is T1x, T1y, T2's x component, and T2's y component, like this. Okay. And now I think you see why, oh, sorry about the glare. Now you see why I generally dislike putting subscripts on things, because now when I break it into components, we also have a fancy word for breaking things into components called resolving forces, right? Resolving vectors, I called it. In this case, we're resolving force vectors, or just resolving forces. So when you have a subscript, once you resolve the force, it just makes things messy. So this is copied from one of it's not from this book, but from another worksheet. And we'll just use the same notations. But if it's up to if I get my choice in drawing things or labeling things, I tend to avoid subscripts. Otherwise, you probably noticed this already when your textbook would draw a force of gravity this way, and then once you resolve it, you have FGX, FGY, and it starts to get more confusing than it really needs to be. I usually just call it G for gravity, GXGY. That's clean enough. All right, side note aside, focus back on here. All right, so to resolve this vectors, or these two vectors, let's use a different color, right? We'll draw down here and here to see how many units go to the right and how many units upwards, right? So we have 30 degrees here. I don't know if you can see that clearly, but let me just draw that out a little bit more, right? So let me enlarge this T1. Okay, so I'm given that it's 30 degrees over here and 10 units or 10 newtons this way. So T1x is here, right? So it goes this much to the right and this much upwards. So T1y. Which one is cosine, which one is sine, right? The one that is sandwiching the angle is cosine. So T1y is going to be 10 times cosine 30. Now I'm going to show you in what you can do immediately in an exam is directly write this over here. T1y is T1, so 10 is T1. So the magnitude of T1 times cosine 30 degrees. And T1x is T1 times sine of 30 degrees, because one is going to be cosine, one is going to be sine. You can double check. It's always good to do a double check. What's sine 30? Sine 30 is this over this, right? It's opposite over hypotenuse. So this one is going to be the denominator times sine of 30 degrees. So sine is always the opposite, and cosine is always the one that's sandwiching it. Okay, and let's move on to T2 x. I'm going to draw it separately as well, but as you gain more and more confidence, you can directly do it on here. Yeah, I'll do it separately just as we're gaining confidence along the way. So this is T2, right? So T2 here is 20, and let's resolve it into its components. So it's this much is T2y, this is T2x. Okay, so and we're also given this is 60 degrees. So T2y again is the cosine because it's sandwiching the angle. So T2y is T2 cosine 30 degrees and T2 sine 30 degrees. All right, and now let's plug in the numbers. T1 is 10, sorry, yeah, so 10 sine 30 degrees, again, very famous angle. I know that it's exactly 1/2. And cosine 30, if you've seen this enough times, you know it's square root of 3/2, and this T2 is 20 times, again, 1/2, and 20 times square root of 3/2. Okay. And now it's time to pull out your calculator and plug it in, but I think some of them is easy, right? That's 5. Oh, I should check. Did you see one thing I almost forgot to do? I need to check the signs. So we should do that, right? So when we put it over here, T1x is going in a positive x direction and positive y direction. So that's all fine. And T2 is going in the negative x direction and a positive y direction. Right? Let me say that again, negative x, positive y. So T2x needs to be a negative number. Okay, so it has to, I will need an extra negative sign in front over here. Okay, so the x, adding up the x is 5, and this, I'll need a calculator, but this is easy, so minus 10. Okay, and we will again pull out our calculator. You know how to do that. I'll just skip to the answer. Okay, we're back. So I got 8.66. You can double check that on your calculator as well to make sure I got it right. And 17.3. Have 3 significant figures. I think that's good. Okay, and now we can just add these together. So I have minus 5, and this would be 23.96. Okay. By 23, I mean 25. Okay, so you can double check all that. Are we done? Well, no, not yet, because we want magnitude and direction. If you would like, just put in the newtons here. And yeah, let's find the magnitude and direction. Okay. And I shouldn't have erased that because I should remember to do this. You always want to sketch a diagram first, right? So how would that look? Let's sketch it over here. Minus 5, so 1, 2, 3, 4, 5, and then positive 25. So it's going very much towards the front and just a little bit to the left, and it's in the negative x direction. Okay, so this is the net force, and you want to ask yourself, does that make sense? So if I hadn't erased it, we had T1 this way and T2 this way, right? 30 degrees and 60 degrees. Now, if I geometrically add them together, so move T1 all the way from head to tail over here, right? So that's roughly right. And this is half of the length of T2. Right? T1's half of the length, but pointing that way, and sort of half of the angle of that. So it should be that. And if I draw a thicker line, straight enough, I guess, we'll work with that. And that should be F net. Does that look just sort of about right? Yeah, I think so. That's close enough. So that gives you a good reassurance, all right? And it's also now useful in finding the magnitude, right? So how many units this way? I know it's -5, but what's the length? The length is 5. And what's the height? What's the length over here? The height is 25.96. So let's do a Pythagoras theorem, and I'll be right back with you. Okay, so I got the numbers. So the magnitude of F net without a vector, right, is 25.96 squared plus 5 squared square root. And that is, from what I got, 26.43. And at the end, let's just leave it with 3 significant figures or 1 decimal place. That's good enough. Okay. Okay. Are we done? No. Direction, right? So the direction, and yeah, let's make sure we understand which ways the X and Y. Which angle should we? You have choices. You can either give this angle, or you can give the polar angle, which is from all the way to the right. Let's do both, right? So let's do this one. Theta. So the direction is tangent theta is opposite over adjacent, right? So that's 5. Sorry, I don't know if you can see this, right? So that length over there is 5. That length over here is 25.96. So tangent is opposite over adjacent, 25.96. Okay, so that will tell me theta is arctangent of 5 over 25.96, and I will have, let's do this, arctangent, maybe I can share with you as well. So we have arctangent of 5 divided by 25.96, and I get 10.9, so that should be 10.9 degrees, and always good to check you are indeed in degrees, so that's good. Okay, so 10.9 degrees. Okay, is that all? Not quite, right? So you want to also specify it clearly. So that's 10.9 degrees counterclockwise from the positive y-axis. Okay, underline or box your work. That's your complete answer. Okay. Now give you a couple of options and a few comments as well. Is if you like, you can give things in polar angle, but just clarify it is a polar angle. So polar angle measures from the positive x-axis all the way to there. So you need to add an extra right angle over there, so 90 degrees. So alternatively, you can write an extra line if you want to do an extra work of adding that 90 degrees. Then you can write it has a polar angle of theta equals to, add 90 to that. So that's 100, right? 100. You can use a calculator, but that's easy enough. 100.9 degrees. Okay. So if you want to do some extra work and do that, that's also fine. And I usually just leave it that way. All right. Couple of quick comments as well. In terms of notation, just be careful. It's always good to keep track of things. Is whenever you have vectors, right? So when you have a vector, it usually comes with components. If you have no vector sign over here, it usually is a scalar. Okay. Yeah. So we'll see how this fits in with the one-dimensional example as well, and also do one more example to familiarize yourself with this. Okay.